let me introduce yet another jargon in context of matrices. So if I have, let's say, two matrices P and Q of the same order, square matrices, two matrices P and Q of the same order. Two square matrices P and Q of the same order. If P into Q is IN, IN is an identity matrix. If P into Q is IN, which is an identity matrix, then we say P and Q are inverses of each other. We then say P and Q are inverses of each other. That means we write this as P equal to Q inverse. P is Q inverse, and we say Q is P inverse. They are said to be inverses of each other. We then say P is Q inverse and Q is P inverse. It's not P to power minus 1. It's P inverse. Inverse is an operator. In this case, minus 1 is not a number. It's an operation. It's an operation. Right? So, Q is said to be the inverse of P because Q when multiplied with P gives me an identity matrix. And this will also be equal to Q into P. Does not matter the order in this. They will commute. They would commute. They are then called inverses of each other. The inverse of P is Q. The inverse of Q is P. Know what I'm saying? So, P in this case you can write as Q inverse. So, Q inverse into Q is an identity matrix. This is the same as Q into Q inverse. That's Q into this P is Q inverse. P is Q inverse. That's going to be an identity matrix. Same thing. Same. P inverse P. Actually, it's the same thing. It's the same thing. I could have written Q as P inverse. So, P into P inverse is IN. P into P inverse is IN. How to find the inverse of a matrix? Let me come to that. What operation would be required to find the inverse? Given a matrix P, how to find its inverse? So, when I say find the inverse of a matrix, what it means is find a matrix which when multiplied with the given matrix produces an identity matrix. Now, how to find such a matrix is another ball game. I'm coming to that. First of all, understand what an inverse means. Right? Now, also you would realize if P is a matrix, this is its inverse. This is its inverse. They are inverses of each other. The inverse of P is this, and the inverse of P inverse will be this. They are inverses of each other. Right? The inverse of this is P inverse, and the inverse of this is also a matrix after all. This is also a matrix after all. The inverse of this will be this. That means P inverse will be P. A inverse will be A. Do you understand that? They are inverses of each other. The inverse of P is this, and the inverse of P inverse will be P. Yes or no? You know what I'm saying? Now don't multiply these powers. It's an operation. In this case, minus 1 is an operator. It's not a number. Right? Now, let us see how to find, let us see how to find the inverse of a matrix. How to find the inverse of a matrix, and will inverse always exist? That's a question. For every matrix, can I necessarily find an inverse? If no, when would I not be able to find the inverse? If yes, what would be the necessary and sufficient condition for the inverse of a matrix to exist? Right? Now, A is a square matrix. A adjoint A is determinant A, which is a scalar, into In. Yes or no? Can I divide by determinant A? Only if A is non-singular. That means if determinant A is not 0, then I can divide by determinant A, not by A, by determinant A. If A is non-singular, then A into adjoint A by determinant A. This determinant A is a scalar. Every entry of adjoint A gets divided by a scalar, which is determinant A. This is what this means. That's equal to In. Provided determinant A is not 0. Yes or no? Which means, if A is multiplied with this, I get an identity matrix. That means this must be the inverse of A. This must be the inverse of A. Yes or no? But when will it exist? It will exist if determinant A is not 0. If A is non-singular, you will have inverse of matrices if they are non-singular. Right? So I could look upon this adjoint A by determinant A as A inverse. Find the adjoint of a matrix. How do you find the adjoint of a matrix? Take the matrix of cofactors and transpose that. That will give you adjoint of that matrix. And then divide that matrix, every entry of that matrix, by determinant A. A scalar, you get A inverse. Yes or no? That's what A inverse is. Yes or no? So, one, if two matrices are inverses of each other, then their product will always be an identity matrix. Their product will always be an identity matrix. Does not matter the order. Does not matter the order. Now, in connection with this inverse, there is an important property which is almost used like staple food. Can I wipe this off? A is a square matrix. B is another square matrix of the same order. Their product would also be a matrix. Their product will also be a matrix. And if I have to find the inverse of the product, then this will be equal to B inverse A inverse. The method of the rule of reversals will hold good. It will be the inverse of B into inverse of A. Let's see how to establish this. Hey. For sure, if this has to be true, that means AB and B inverse A inverse. Very clearly, the inverse of AB is this. The inverse of AB is this. That means AB and B inverse A inverse are inverses of each other, inverses of each other. AB and B inverse A inverse should be inverses of each other, only then it can happen. Yes or no? Now that means if I multiply these two and I get an identity matrix, then they would be inverses of each other. The inverse of this will be this, and the inverse of this will be this. If their product is an identity matrix, then they will be inverses of each other. Right? Let's look at their product. AB into B inverse A inverse. For them, for these two matrices to be inverses of each other, their product must be an identity matrix. right? Now, in multiplication, rule of associativity holds, right? So I could rearrange this A into B inverse, A inverse. I could put brackets at will in a multiplication. Did I tell you this property? But B inverse would be an identity matrix. B into inverse of B would be an identity matrix. Yes or no? A matrix into its inverse will be an identity matrix. So B into B inverse would be IN. Yes or no? So this is going to be A times IN into A inverse. Yes or no? Confused? But when IN is multiplied with A inverse, it will give me A inverse only, isn't it? When IN is multiplied with a matrix, it will give me that matrix. So this is going to be A. IN into A inverse will be the matrix A inverse. But A inverse would be IN. Matrix into its inverse is going to be IN. So that's going to be IN, which means AB and B inverse A inverse are inverses of each other. The inverse of this will be this, and the inverse of this will be this. That means AB, the inverse of AB is B inverse A inverse. B inverse A inverse. Get mentally acclimatized to the linear algebraic ways, right? AB inverse would be, so again, reversal. It happened in transpose also. AB transpose was B transpose into A transpose. Adjoint AB was adjoint B into adjoint A, right? So AB inverse would be B inverse A inverse. Yes or no? This is a very commonly used property for inverses. The other property which I would think is very important. Can I wipe this off? A transpose, inverse of A transpose would be A inverse transpose. A transpose when inverse is the same as A inverse when transposed. That means transpose and inverse operators are interchangeable. Transpose and inverse operators are interchangeable operators. You know what I'm saying? Are interchangeable operators. How? Now, look, if the inverse of A transpose is A inverse transpose, right? This is the inverse of A transpose. If the inverse of this is this, if the inverse of this is this, then the product of these two must be an identity matrix, right? If the inverse of this is this, then their product must be an identity matrix. So if I can establish that the product is an identity matrix, then the inverse of this must be this. Yes or no? Right? So let me look at the product of these two matrices, A transpose, A inverse transpose. All right. I want to establish that this is an identity matrix. Then these two matrices would be inverses of each other. Inverse of this will be this, and inverse of this will be this. This would then hold good. Now, do you remember? AB transpose is B transpose into A transpose. So this is like some A transpose into B transpose. This is like A transpose into B transpose. That's going to be BA transpose. That's going to be BA transpose, yes or no? So that's going to be A inverse A transposed. Yes or no? But A inverse A is I. A inverse A is I. And IN when transposed will be IN. If an identity matrix is transposed, it will remain unaltered. Yes or no? So it will retain status. It will retain status. Sounds good? A inverse A is I, and when an identity matrix, a diagonal matrix is transposed, it'll look the same, right? So IN transpose will always be IN, right?